Hello guys, welcome back. Today we will see how to simulate plant in Houdini. For this tutorial we will use RBD and Vellum solver to simulate this effect. As you can see on my screen, I have created this effect using RBD and Vellum, and currently I have only simulated this area, but if you need, you can simulate overall this plant with this method. And also this method is fully procedural. So take a geometry node and let's name it as impact tree. I will give this tree link in the description. You can download it for free.
Yes. So
This is the tree model. I got this tree from my friend, and I think he downloaded from JZ tree asset, something like that. I don't remember. We will simulate only this area for now for this tutorial, but you can replicate this whole process on the whole tree. So first we will simulate the branches. So for the branches we have some groups here, like these groups. We can isolate that and we can click on delete non-selected. So these are our branches. Now we only need this area for now, so take a split node and let's delete that based on PID. No, not PID, I think ID. Yeah. So you can select lasso tool and select that area. So for now we will only simulate this part. Let's increase the anti-aliasing sample so we will get better details on the viewport. Now we will fracture this tree first. So to fracture it we will use simple Voronoi fracture. So take a scatter node and scatter it around 110 points, and then take a Voronoi fracture. So for now there will be some point which will be extremely close to each other. So to fix that we can use a fuse node. Currently there is no point which are extremely close, but might be in case if you have some other geometry, then few points will be extremely close. So to fix that you can use fuse node and increase the snap distance to around 0.2, and then connect this to Voronoi fracture. And if you take a exploded view, you can see our pieces will look something like this. So what we need to do now, we can take a convex decomposition node and we will turn this high-res geometry into a convex geometry. As you know, RBD solver reads convex geometry much faster as compared to our regular geometry. So let's concavity to 0.15. So we will have some better shapes. So this will be our proxy pieces. Now we need to create name attribute. We already have name attribute here, so we will turn off this name attribute and we will turn on create pack fragments. Now we need to set up some initial attributes like active and inactive. So take a attribute wrangle, and first we will set active is equal to 1. So our whole pieces will be active. But if the whole pieces is active, then all the branch will get fallen down. So to fix that, we can take a group node and we can select this area and make it inactive. So to do that, we can choose here like inact. We can name the group as inactive, and here in the group type, select points, turn off base group and turn on bounding region. We have to choose bounding box, and then we can increase this bound. Let's make the background darker, and we can like this, we can make this piece as inactive. Now duplicate this wrangle, and here in the group we have to choose inactive, and we can make the inactive value to 0. Now we need to create constraint for it. This one we will use soft constraint. As you know, the soft constraint are bouncy in nature, and it will not break unless and until you give some condition to it. As compared to glue, if the glue get collide to anything, it will get break. In soft, it is not like that. The soft will get damp here and there, but it will not break. As you know, the wood also behave something like that only. Whenever something collision happen, it gets damping moment here and there, and then it's get to its rest position. So we will use same method here also. So to do that, we can take connect adjacent pieces node, and here in the connection type we can choose adjacent pieces from surface point. So here now we will have constraint something like this, and we have to increase the constraint connection, and here in the constraint connection, connection we can make it 5. So now the problem is if you know the soft constraint get expand if we directly feed this. So to fix that, what we can do, we can take a RBD convert constraint node, and here we in the first geometry we will connect our proxy pieces, and in the second one we will connect our constraint. Now you see our constraint look like this here, but here we will make this constraint as a surface point constraint like this. If I turn on take a null, you can see it is look like this. Now we can take RBD constraint properties node, and we can set the constraint properties. So here in the constraint type, select soft, and in the stiffness we will set the stiffness value to 150, and we will keep the rest of the thing default. Now take a DOP network, connect this and this into first input, or else you can connect directly here. Dive inside it and take a RBD pack object. Take a RBD pack object. Here in the geometry source, select first context of geometry and take a rigid body solver. and take a gravity force. Now if we play, you will see it play properly. It is falling. So now we don't have a constraint right now in our solver, so let's import our constraint as well. Take a constraint network node and bullet soft constraint relationship. In the constraint network, select the geometry source as second input context geometry. Now if I play this, it will be behaving weirdly. It is happening because here our rest lengths have been scaled down to 0, but in the constraint node it is still set to 1, so we have to make the rest length value to 0. Now if I play this, it will not behave weirdly, but since our gravity force is too much, this tree will fall down. So let's decrease the gravity value to 0.1, not 0.1, -1. And if I play this, it will not fall too much down. So as you can see here, it's look natural to me. Now what we can do, we can take a sphere node for the collision, and we can set the sphere collision to scale to 1.8, and we can take a transform node. Here we can animate this rotation value, so it will have some animation to it. If you see, it will have animation. And now what we can do, animate this sphere going from here to can make it here like this, so it will have. Now let's move it to something here, so our tree will get enough collision. Now take a null node and name it as collider. Copy this null and dive inside it. Take a static object node and a merge node, connect it here. Let's make sure to change the input to first in the merge node. Here in the soft path, paste our null object and turn on use deforming geometry. Here in the collision, go to bullet data. Instead of convex hull, we gonna choose sphere. Now if I turn on the simulation, you can see so it currently it is damping too much, so we can damping moment and add some drag force to it. So here in the constraint node, reduce the damping ratio to 0.1 and take a pop drag node, set the air resistance to 0.7. Now let's play this and see how it is looking. Okay, I think we have to move the sphere little bit more up. Disable the simulation and make it more up. Now reset the sim. Now we can cache this. Take a DOP import node and we will import RBD. Here we will create point to represent the object, and then we can bring our Voronoi fracture and take a transform pieces node here. And in the second input we can connect our DOP import, and in the third one we can connect the rest frame, which will be our first frame. So now we can have this. So as you can see here, when the ball goes up, let's cache this first. We can take a file cache node, and so now if you see, our tree sim look like this, and it have a nice damping movement. And now the problem is, if you see, our trees are fractured pieces and it is getting break. So to fix this we can use point deform as well, but I don't prefer using point deform. Instead I use this wrap node. As you can see on my other tutorials also, like on CFX tutorials, I have been using this node. So this node is for free. I will give the link in the description. You can download it for free, and we will use this wrap node to deform this. So it is same like point deform only. So here in the second we need to give rest position, and in the third we will give the driver. So now if you see, our that issue have been gone, but there is some problem. Like here you can see it have been expanded. So to fix that we can as you know, we already here have ID attribute, and here also we have. So we can go in override tab and click on enable, and here instead of piece attribute we will choose ID. So it will take few time, and but the problem is we have ID here also and on the point level also. So we can delete the point ID, like here point, and we can delete the PID as well, and here also we can do the same, and then we can choose this. And now here you can go in general tab and increase this iteration to 6, and you can turn the mode to Lapican. Now it will have nice joint movement, and this will be our branch sim, and from this simulation we will derive the leaves and falling leaves. So here we will split this blast and split node, turn off delete non-selected, and we will simulate only these leaves. But you see here it is currently pack geometry and we have to unpack it. So if I unpack it and if I take a unpack node, so now it is pack fragments. Here we have to transfer all the attributes because it has UV and other data co-view, and then we have to take another unpack node and here we can see only these leaves have around 1.5 lakh polygons. So if we will simulate whole these leaves at once, then it will gonna take ages to simulate. So we will go for wedging method. So to do that, what we can do, first let's optimize the geometry. We will keep all the attributes and delete this detail attributes. Then we will add a connectivity first on primitive level. Now we have class attribute which we will use for wrapping the leaves based on pairing attribute. So after this, now we have to create cluster attribute. So if we create cluster directly here, then it will cause some problem. So to create cluster in proper way, first we can create name attribute, and here we have to turn off connect inside edges, and then here we will again take a assemble node, and here we will turn off name attribute and we will turn on create pack fragments. Now you can see we have 19.7k fragments. Here we will delete. Here we have to transfer the attribute name. Now if you see, we have name on point and primitive both, so we have to delete the name from point level. Now we have only on primitive. Now we can take cluster node, and if I turn on this cluster, it is not visible because it is currently packed. So we can take attribute copy node and connect it here. Here we will turn on match by attribute. We will give name. Since name is on primitive level, we have to change the group type to primitive on both. Now here in the attribute name we will choose cluster. Now if you see, we have cluster, and the cluster is around 9-10 clusters. So first we will simulate this part, then this, and it will be fully procedural. So if you need to simulate the whole tree, then you can follow this method. It will work easily. Now we have to cache this first, or else it will calculate again and again, and we can name this cluster cache. We have to save only one frame, so turn off time dependent and click on save to disk. Now what we need to do is, here if you see, here we can take an attribute wrangle node, and we have to write this code. So now if increase this value, you can see we can extract each cluster over here. So we will use this parameter in wedge to cache based on wedge. Now take an attribute delete node, and we have to delete everything except curve view, cluster, and class UV. So we have some optimized geometry. Now take a group node. We can connect this on the split. We will use this to get the pinpoints so we can attach the leaves to the branches. So here in the group, set the group type to point. Here in PTS, turn on base group and turn on bounding region, and we have to choose bounding object. Now we can take a peak node and we can increase the peak distance to 0.01. So now our leaves will get attached. Now we can take poly reduce node and now we can reduce to 33%. Now we can take Vellum cloth node and we can decrease the density and edge length scale to 0.01 and 0.1, and then we don't have to change anything here. We just need to turn on this scale by attribute, and here we will use curve view. As you know, here we already have curve view attribute, so we will use that attribute to get the bend stiffness value. Now rest everything we can keep default. Now we have to take attach to geometry, and here in the third input we have to connect our branch, and here we can choose it will be attached on the first frame only. So we will attach the whole leaves for now, and on this simulation we will only get the leaves movement. For the falling leaves we will create another simulation for that. So let's play it. Now if you see, it will be a bit fast, and so leaves will look something like this. We can decrease the gravity to -2 and substeps to 2 if you need, but so now we have to set our wedge. So first take a Vellum post process node, and now we have to choose labs file cache. Labs file cache, not the default file cache. We have to choose this lab file cache, and here we have to click on wedging, and what we need to do is here instead of evaluate as, we will choose custom range, and as you know, we have 10 clustered. So here in the wedge count we will keep the value 10, and number of attributes will be only 1 because we will use a cluster attribute. So here write cluster, and instead of automatic we will choose custom range, and our value goes from 0 to 9, so we will keep 0 and the maximum will be 9. So now if you see, if I click on this point 1, then you can see our cluster is 0 here, and here it will be 3, and it will go till 9, and our cluster attribute is cluster. So here in the attribute triangle on the cluster parameter we can type at cluster, because now the cluster is a global variable. So now if I click on this, then you can see this value changes to 9. If I click this, then it will automatically get changed to different cluster. If I click on this, then it will change. So by this method you can wedge it. So for now I will only simulate 5 wedges, but you can simulate the whole one. And to simulate properly we have to first, let's save it and go in scheduling. So currently my PC has 32 cores, so I will choose a CPU count to use. Total counts less than 1, and I will also turn on this and I will give per simulation 31 CPUs, so my simulation will be much faster. And now then we can click save in background, so it will save. The wedging will start in few minutes. So I have cached all the wedges here because the wedges sim only took 10 to 15 minutes in my PC, so I cache all the 10 wedges. So now to load the wedges, what you need to do is you need to expand this load tab, and then here wedges to merge you have to turn on this, and here you have to choose all wedges. So now you can see all the wedges has been merged into one cache. Now we need to deform the original leaves with this simulation. So to do that we need to take a wrap node here, a time shift, need to freeze the first frame, and then connect animated into the third input, and the first input will go to our file cache node, the cluster cache, and then we have to display this. Here if you see there will be some stretching issue, if I'm not wrong. You might face some problem. As you can see here, this is the problem I was saying. So to fix this you can go in override tab, click on enable, and here you have to choose class attribute. Now you can see that issue has been resolved. Now only the first time it will take a time to load, and then it will deform faster. So now you can add a null node here in leaves. Now we have to do the funnel leaf simulation as well. So to do that we just need to duplicate this whole network here. and duplicate it. Now go to manual mode, and here we don't need this cluster part. Instead of this, we have to use another wrangle node and turn off this, or else you can delete that. Here we will delete randomly based on class attribute. So to do that, first since we have class attribute on the primitive level, so set the run over type to primitive, and here if we will write a random function I@class is greater than given threshold, remove, we will use prim function, remove prim. We have to remove the primitive from the first input, so we will write 0, and here we will give the prim number and the primitive index. So if I click on this and I will increase this, you can see our primitives have been deleting. So here set the value to 0.04. So this will be our falling leaves. We will make this leaf to fall based on the threshold. So keep all the parameters same. We don't have to change anything here. Just go in the Vellum attach node, and here we have to turn on this output group. In the Vellum attach node, we have to turn on this output group and name this as a break group. Now go inside the solver node. What you can do is take a Vellum constraint property node. Here in the group we have to choose break. Now we have to turn on this break threshold and this break type. Since we need to break the stretch constraint, so here we will choose break type is equal to stretch. So here we will write a fit range parameter, but before that we have to do a few changes on the solver. Like here in the gravity, let's make the value default and increase the simulation memory. Here we don't need to change anything. Now go inside it. Let's play the simulation and see how this looks. Currently the leaves will not fall down even after the impact. To make it fall, we need to do few things here. First, in the break threshold, we need to animate the threshold value. Before that, let's see on which frame the impact is happening. So here it is on frame 59. So we will animate the threshold value from 55 to 59. So to do that, we have to write fit range, and we need to fit between the frame 55 to 59. Our default value will be 0.1 and then 0.0001. So let's see whether it is breaking or not. Okay, we need to give point here. So let's see now. It is breaking, as you can see, but currently all the leaves are getting fallen down. We don't need all the leaves to get fall down, so we will increase this by 0.00025, and now again simulate it and see. We need to add some spin movement also, because you can see the leaves are falling straight, so we can add pop drag spin node. Here we can increase the goal axis to 1 on all the axes, and we can increase the goal spin to 1000, and we can also add pop drag force, and we can set the air resistance to half. Now if you see, now this is looking much better, and we also have some swirly movement on the leaves. You can also add some pop wind if you want the leaves should get noisy flow, so you can do that. And here we don't need to cast base on the wedge, so we can turn off wedge here, and we can have here falling leaves. And the same setup will work for the falling leaves as well. We don't need to change anything. It will just take few minutes to get pairing attribute attached, and after that we can here we need to connect this to attribute wrangle. So now you can see it is behaving like this. Now we can merge, we can also connect our branches here, and so thank you guys for watching. If you like this tutorial, make sure to hit the like and subscribe button. Also you can support me on Patreon.